is our first KCS talk for this semester. And our speaker today is Dr. Xiao. His first name is Yan. Okay. And the title of his talk is Fault, as you can see here, Fault-Tolerant Consensus and its applications in emerging decentralized systems. Okay. This work is the core of Dr. Xiao's new grant. Okay. New grant. That has been announced by Dr. Right? So we'll give Dr. Xiao the stage. Okay. We'll give you 50 minutes and keep the last few minutes for questions. All right. Thank you very much.
All right, thank you for the introduction. So I think by the end of the talk, you will be amazed why I'm doing this 40 years old topic for my own application. So today's talk is basically a tutorial on this topic. If you are familiar with distributed systems, you should be what I'm talking about. So at the last 10 minutes, I'll describe what I'm doing, excuse me, what we are doing in our lab. So what is consensus? Consensus is an ages-old problem, right? So the human history, as long as we have the ancient republic, we had consensus. So by the way, these images are created with using ChatGPT, by the way. So consensus was a problem for millenniums. So until we have modern computers and Bitcoins. So consensus suddenly makes sense because we want to deal with the decentralized internet, which began in the 1960s. So in this talk, I will mainly go over from a historic perspective on what is consensus and why they are useful in computer systems when we're dealing with decentralized scenario and threats. So the first problem we consider is the very well-known Byzantine generals problem. So this idea was conceived by the computer scientist Leslie Lamport in 1982. He was a very famous guy, started from Microsoft Research. So the problem basically says you have a group of generals, they want to siege a fortress of an enemy, but the problem is they don't have a predetermined action in the first place. Some wants to attack, some wants to retreat, but the idea for them is to agree on the same action. They can only communicate through messengers by pigeons, whatever. So the threat is half of them are compromised, meaning that they can deliver arbitrary information to others, and they can behave arbitrarily as well. So the conflicting info behavior is known as equivocation. So under this scenario, the success condition for them is all the loyal ones agree on the same action to attack, to retreat. So on the first glance, this is kind of like a voting problem, right? If you imagine that if we have an honest majority, the honest majority should agree on the same action. But the story is not that simple. So to give you a simple case, let's assume where F is 1 and N is 3. So N is the number of people, and F is the number of malicious generals. So in the first case, let's assume that the two of them propose the same action, attack and attack. So we don't care the malicious general does because we assume it will equivocate by default. So in this case, they will succeed because the two loyal ones agree on the same action, attacks. But let's consider the second case when they propose different actions in the first place. So in that case, if we judge by the majority of votes, so the left one will agree on what? Will agree on attack. The right one will decide on retreat. So in this case, we had a failure. So which means this consensus is a failure. We don't have consensus. And as you ask why no consensus means failure, it's because in a military setting, if you don't have consensus, a half-hearted attack will be defeat. So that's the case for most of our settings. All the loyal ones should agree on same action. So the question is there a condition for guaranteed success. So honestly, obviously, we have seen that this 1/2 or condition is not enough. So we have an impossibility result. It is that the agreement is not always achievable if n is less than or equal to 3f. So basically, if you have a room of 3 people, one of them is equivocating, then you don't have consensus. So this is kind of a counterintuitive, but it makes sense. Except that this one guy, everybody can shout out, so it's broadcast, then this is achievable. But in the BGP setting, we don't have such broadcast or syndicated broadcast setting because every pair communicate by messengers. So the proof can be complicated, but basically we go from the basic condition proved by induction all the way go to general case. So we can show the proof in the past. But the next question is is agreement always achievable if n is greater than or equal to 3f plus 1? So if you look at the converse of the condition, say when f is 1, n is 4, f is 2, n is 7, all the way, go to larger f's, can we guarantee the consensus among the loyal generals? So the answer is yes. To do so, we can just prove by construction. So the name is the oral messaging algorithm, which was given by Lamport in his own paper, in the same Byzantine generals problem paper. So here is the algorithm. So you don't have to read in details, but basically observe one thing, which is the recursion they have to take as a commander. So the algorithm itself classifies the generals into 2 types, commander and lieutenants. So it doesn't matter who is the commander as long as it starts the protocol. So it says on the top level of the recursion or the entrance of the function that commander sends its value to all lieutenants, and each lieutenant I acts as its own commander for a new algorithm session OMF-1. So it's the first recursion you have seen here. And at the end of when the recursion function returns a value, each lieutenant I stores the value sent by other lieutenants and decides this majority. So basically, the process, if you want to linearize this recursive function, it may take you some time, but I want to give you an example on how it works and demonstrates the termination, how many recursions it terminates. So let's assume the commander is compromised. And a compromised commander will equivocate, let's assume by default. So the commander starts OM1, the first layer of the function, and the next thing to do is for the lieutenants, they will start their own OM0 function, so by doing this. So by serving as a commander on themselves, each lieutenant will relay their function, their value to other lieutenants and faithfully, because we assume the commander is malicious, so the remaining n-1 lieutenants are honest. So in this case, after relaying, each lieutenant will have a majority decision. So because 1 and 1, 1, 1, 0 is the case for everybody, so the decision will be 1. So 1 means attack, let's assume. So in this case, they have consensus. Remember that the consensus condition is for the loyal ones to agree on something. We don't care what the malicious one think or does, right? So if we go to the second case, when we assume a compromised lieutenant, then we can do the similar process that the honest commander will not equivocate. Let's assume they provide 1, 1, 1 to everybody. So the malicious lieutenant acting as commander will relay different values, 1 and 0. But even by doing this, as you can see that the simple majority decision will allow the blue ones having the same decision. So here we just assume the commander is honest. He will just follow his own proposed value, which is 1. So this actually implies one thing, that as long as the commander is honest and propose something, and that proposed value will eventually be the decision of everybody. So this is actually very good guarantee from Leslie Lamport in his original paper. So, but on the downside, this algorithm is very costly. As you can see, it has f plus 1 recursions, and every recursion takes about n communication messages. So the f recursion, and so basically means the messages, the number of messages will exceed the n to the power of f plus 1. So this is a very complicated recursive algorithm, and I believe nobody used that. So I will show you that there are practical algorithms realizing the same property, but with way fewer communication messages. So at this moment, we have discussed the middle age problem of Byzantine generals problem, and see that whenever n is larger than or equal to 3f plus 1, we have a solution. But now let's travel back to our modern age. From the middle age, we are dealing with computers. So in computers, we are talking about, so the terminology at that time, it was processes. So I think if you are in 270, we are still using this term. So we have n processes or nodes. F out of them may be faulty. So faulty is actually a big term, covers everything we want to discuss, from the crash fault to Byzantine fault. The Byzantine fault is actually the Byzantine generals problems case that the bad guy can do anything. So if you look at their relationship, Byzantine behavior actually covers crash failure, because arbitrariness means everything, means anything, right? So it covers crash. So on the flip side, if we make the arguments from the other direction, if a protocol achieves crash fault tolerance, which means it will tolerate f crash faults among the n nodes to achieve consensus, to allow the loyal ones to agree on something. So this protocol is known as the crash fault tolerant protocol, CFT. So similarly, the BFT protocol is known as the protocol can tolerate f Byzantine faulty nodes to achieve consensus, and then naturally, a BFT protocol is a CFT one. So because if you can tolerate the Byzantine faults, and naturally you can tolerate crash faults. This is the reverse condition. So the fundamental results from the literature is, for CFT, we only require n is larger than or equal to 2f plus 1. For BFT, we still follow the same impossibility results from the Byzantine generals problem. We have to have n is no less than 3f plus 1. So this is the default condition for almost every research ideas. But there is some exception case. Like I said, in this big room, if we just communicate loudly, which means everybody's statements can be heard by everybody else, so this is known as a synchronous authenticated condition. So if you have synchronous authenticated condition, you only need f is no smaller than 2f plus 1. So this is a rare case, which is not possible in the internet, because in the internet sometimes you have to have, there's no direct biological acoustic channels for you to achieve such condition. But we can simulate that if we can sit together and talk. So at this moment, we have covered actually the basic foundation of consensus or agreement. But what is consensus in a rigorous term, right? So you may think that consensus means agreement, but in computer terms, it's not just agreement. The first requirement is actually termination, because a computer system have to be responsive to requests. We are doing a service to other people, so which means response time has to be finite. So to translate that into distributed systems terms, which means every correct process eventually produce an output, so it cannot be undecided all the time. So the second is actually agreement. We have seen before that every correct or loyal process decides the same value, let's say output y hat. And the last one is known as the validity. So if every process begins with the same inputs as say x hat, then this decision value y hat should be y hat, should be x hat. So this looks strange to you because why should we have this? The reason behind this requirement is we want to avoid trivial decisions, because there are some the machines, if I can store a pre-stored default value for y, this will be their decision, and they can even be honest. So we want to avoid that trivial scenarios that the value we decided should come from an honest proposal. So that's the validity decision tells us. So based on these conditions, 3 conditions, we are almost ready to study more consensus protocols, because these conditions are formulated from the early 1980s, and all the following protocols will use these 3 conditions. Now look back at the Byzantine general's problem with our messaging algorithm. So do we have termination? Yeah, because this is a recursive algorithm, it guarantees termination, right? So it has f recursions plus the first entrance, we have f plus, so total message complexity is n to the power of f plus 1. And do we have agreement? The answer is obvious, right? We have demonstrated. Do we have validity? The answer is also yes. So if we assume the commander has proposed something, then we guarantee that every lieutenant will agree on the same proposed value. So those are, and if the commander is malicious, the lieutenants can still propose something, they will agree on the same value. So basically, to be short, our message algorithm achieves this so-called 3 requirements of Byzantine consensus. So now we have this stop for the basic construction and move a little bit further to our computing setting. So because if we just talk about the agreement on the values, it doesn't make any practical sense, right? Because a computer system has to serve requests, have to serve the clients. So according to Wikipedia, there is a subtle difference between distributed computing and distributed systems. So for computing, you have to agree on some data value that is needed for during the computation. So to give you a little bit my personal insight, a distributed computing requires a server consortium that answers requests from external clients. So the clients may have a sequence of requests that they have to be executed in the same order. A different order of the requests will give you trouble. You can just assume that they have some causal order between the requests. So the server has to process them in the same order that the processed results will be returned back to the client. So to solve this issue, the prior work has proposed 2 basic foundations, very similar to our consensus requirements, but they have different emphasis. So for safety, it means every correct server, so here correct means non-faulty, aka loyal. So every correct server must agree on the same order of requests. So the key word is the same order. It's not only the value, but it's the order as well. So which means if the client proposes my second request as a second, then in the server consortium, it also has to be processed as a second request. So this is a total ordering of execution. And for liveness, it means all requests should be executed eventually. So this is basically the same with termination as you have seen before for Byzantine consensus. So the question now is, can we just apply, say, our messaging algorithm to achieve, to realize distributed computing, safety, and liveness? So the answer is actually depends. You can say that we can use Byzantine consensus as a part of this server consortium to achieve this, but they are not rigorously on the same page. So basically, to achieve this, past work has proposed to use this very classic state machine replication. So this is a real simple idea, which means for all the parties to agree on the same order, I just synchronize everything. So the state covers a replicated stuff, a list of requests received, list of requests executed. So if you have the first 2 states, you will naturally have an order, so right, because the list of requests received is more than the list of requests executed. and other control variables such as the number of the global variables, n and f, all those things. So the key idea is the states should be always synchronized before and after executing each request, right? And there's one missing condition I didn't mention here is the execution should be deterministic. Even if they use random numbers, the random numbers should be pseudo-random with the same seed so that it's not truly random from the physical entropy. So this is a key idea for SMR. And how it works on the very high level that applies for every SMR algorithm is that all servers start with the same state, and they do a BFT consensus on the order of each request, and so that agree on the same sequence number of each new request. And they will update the new local state, execute the request, and update the new state as well. So by doing this, at the end of the execution, I'm ready to do the second round of BFT consensus for new requests. So this is a really simplified view on SMR scheme, although different protocols have different designs. So as for more assumptions, by the way, I'm using a lot of texts. You don't have to look at this. I can, for the assumptions, almost all the SMR protocols assume a fully connected network. So I know this may sound suspicious, this sounds not realistic, but in the modern computers, this can be done, particularly when we have TLS security suites that end-to-end communication is possible. So internet is our current day doesn't have too much delay, and we have a guaranteed eventual delivery. And every message is authenticated, proving the origin, and they are not altered. And about delays, we have two modes of delay according to previous work. The first one is full synchrony, which means messages are delivered within a certain round, or in other words, any message can be delivered within the fixed delay delta. And it'll be a lose from synchrony is partial synchrony, meaning that network reaches delta synchrony after some unknown global stabilization time, or GST. You can think of this as your internet router setup case, that not everybody is online in the first place, but when everybody is online from the wakes up from the sleeping, that we should be capable to do synchronous communication. So these two are the most commonly used conditions because our current day internet supports this. So, and later we'll go through something known as the asynchronous communication, which is not common in internet, but it is possible. But the modern SMR protocols mainly deals with these two conditions. So, so for the CFT protocols, I can quickly, we can skip that because CFT protocols are kind of easier to realize because you just require a leader to replicate their own the requests to different servers, replicas, and replicas will send results to a leader, as long as the leader is honest in this case. If the leader is not honest or you don't trust leader, you can use Lamport's 1989 design, which is known as Paxos, so that the clients can do their own majority vote on the decision. But this is actually quite trivial in my opinion. The holy grail is actually to achieve the BFT SMR when you have Byzantine faults, including the leader. So it is proposed by Castro and Liskov at the end of the last century. So it was known for practical efficiency as well. So here I just quickly go over why it is safe, why it is Byzantine fault tolerant without going into too much details. So the leader proposes, or primary proposes a request sequence number, which you can augment your previous number by 1. The replica reach agreement on the proposed request sequence number. So first I see the request from the leader, and then I agree on the leader by this fully connected votes. And the last thing is replicas will again do another round of votes, demonstrating each other's readiness to execute the requests. So this one is very quite subtle because you may want to think that once you have agreements, we are ready to execute, but it's not that simple. But first case, for the prepared case of why we have to have these votes, So in the prepare case, each server collects at least 2f plus 1 votes on the sequence number. So the question is why we should have 2f plus 1 votes on the sequence number for this phase. So because by doing this vote quorum, or the quorum of votes, it will be impossible for other sequence numbers. So to demonstrate that, you can see that the left area is the quorum you have received. Let's assume that another quorum emerges for a different sequence number. So what will happen is the 2f plus 1 and 2f plus 1, they intersect will at least f plus 1, right? So since we assume that there are at most f malicious or f Byzantine nodes in our system, so this intersection will contain at least one honest node. So this one honest node will not equivocate. So by using this contradiction, the second quorum will not emerge, will be impossible. All right. So here basically says that the prepare case is by doing this votes is guaranteed to be agreement. But the next question is why we have to have a second round of quorum votes for commit phase. The reason is we are dealing with practical situations when the system suddenly crashed, or one of the servers crashed right after the prepare case. Then nobody knows should I execute or not execute. Because at the end of the prepare case, I already know I have made this agreement decision, but I don't know if others also made the same decision. So that's why we always require an extra round of finalization to get everybody on the same page, ready to execute. So this is the idea of the second round of commit phase, second round of votes, to make sure that after this commit phase, everybody is able to execute without concern. So this is the key idea of PBFT, the most well-known Byzantine fault-tolerant SMR protocol up to date. Actually, because I was doing blockchain research, people basically equate PBFT with all kinds of BFT protocols. This is untrue. PBFT is just the first of BFT protocols widely used by our community. And also, I can quickly go over that. If the leader is unresponsive, they can incur a leader rotation scheme known as view change, so that the next in line will be the new leader and restart the process. So this is also may happen if in the first view that the commit is not finished. So if you start a new view, you can just rewind the process and start from the prepared phase. So that that's why, as I said, the commitment phase is important to show that if an unexpected leader change happens, we can just your previous agreement can still be used as long as you haven't committed to your execution. So this is basically a very high-level overview on PBFT. So the question is, does PBFT achieve consensus? The answer is obviously yes, but how? So the quick equivalence is that the consensus on the requests and their total order is actually sufficient to provide you SMR, right? Because we assume that a state machine system, every replica's execution is deterministic. As long as you have the same order and all the honest one have the same execution without randomness or without uncontrolled randomness, you will always have the same results. So that's why we can say consensus on the total order of the requests is the equivalent problem of SMR. So AKA, termination can be translated into liveness, agreement and validity can translate to safety. So this is a core idea that you separate the practical people on the right side, and from the theory people on the right side, on the left side, because they use different terminologies. I don't know why they are doing so. And to take this core idea even further, we have this very recent development known as hot stuff. So they are stripping away each replica's responsibility for calculating votes. So every vote is counted by the leader. The leader does 3 rounds of votes, just like the previous one doing 2 rounds of votes, so that at the end of the day, all the replicas will agree on the same preparedness to commit and execute afterwards. So as for more details, I think we have very well-written paper in 2019. So basically, the benefits from this compared to PBFT is the communication is much more efficient. It's ON because it doesn't require peer-wise communication. The leader handles all. But the drawback is whenever you have a leader unresponsiveness, your view change will take further because your leader has a heavier duty on dealing with the votes. All right. So here I can give you a quick summary on all the BFT protocols. It all started with actually Leslie Lamport in 1978 when he proposed this causal consistency work and early SMR ideas. And we have Byzantine generals problem and all the early formulations. So then after that, after we have the SMR formulation ready, proposed in the formalized in the 1990 by somebody known as Schneider. I forgot his full name. But after that, until the end of 1999, there's no practical usage until we have the PBFT in 1999. So after that, in the next 8 years, we have very different PBFT variants proposed, and they were used in database applications. So, but at that time, it is not well known outside this community until Bitcoin. So it was really big blockchain and cryptocurrencies that reinvigorated the interests to PBFT, to BFT protocols from 2008. And suddenly, even though Bitcoin is not designed based on BFT, people were looking back at this huge line of BFT work saying that, oh, this work we can propose much more efficient replacements for Bitcoin's own consensus protocol. But this becomes a huge trend in the last 10 years. So in the next 20 minutes or 15 minutes, I'll discuss what I think, how Bitcoin reflects some of the ideas of SMR, of BFT SMR. So here for the asynchronous condition, we just skip that because asynchrony is a very uncommon situation, except that you have to dealing with this ad hoc scenario when there's no internet at all times. All right, now we come to the discussion of Bitcoin or blockchain. Bitcoin deals with a different problem, actually. It is considered as a distributed computing problem, but it's mainly for payments. So at that time, people were dreaming of a digital cash system, which is anonymous, offline, and counters double spending, because counterfeiting is very hard. When your money is digital, right? It can be copied without any easily. So there are some previous efforts providing digital cash, but unfortunately they failed because they are not scalable, which I think is the most important thing. And in the 1988, when eCash was proposed, it was very promising, but eventually they were competing with credit card companies, so they failed. So and also after that, we have several new proposals, which I think was already very, very close to Bitcoin's proof of work idea, but they are still relying on a single authority for issuing those cash. So the holy grail is that we want to address double spending problem. It's not controlled by a single authority like the Federal Reserve. We don't want that. And it's applicable to all purpose transactions. It's not just for any game tokens or digital tokens. So in 2008, we had Bitcoin. We had this white paper for Bitcoin by a mysterious guy known as Nakamoto. So nobody knows who that is. So why Bitcoin suddenly became a huge trend in this decentralized system field? Because it is decentralized, it is pseudonymous, and it is secure by design. It relies on cryptography. It doesn't rely on central authority or Federal Reserve. So at this moment, you can almost sense that we need consensus, because without consensus, how are you gonna guarantee that everybody has agreed on a payment in a decentralized manner? So blockchain system in a nutshell is basically a network of nodes. A node is considered as a general, or considered as a process in our previous discussion. So it's a peer-to-peer network. They are not always fully connected, but we can use digital signatures to provide authenticity. So all nodes, the aim is for all the nodes to finalize a unique, correct, and immutable blockchain ledger, right? A blockchain ledger you can think of as a serialization of requests, as we discussed earlier for the SMR system. So for the applications, you can have decentralized ID, finance, voting. That's not the concern of our today's talk. We're mainly interested in the consensus algorithm that underpins blockchain's fundamental security. So basically, without consensus, consensus protocol, you don't have the Bitcoin we have today. So, yeah. So the idea is every replica or every node should agree on a common history of transactions. And we are batching the transactions into blocks. So every block contains some transactions, which is known as the transaction ledger for that history. And the blocks are linked by each other through hash links. So in this way, every new block is adding to the previous one. And the aim for the system is everybody should agree on the same linked list of blocks. So this is the very high-level view of blockchain's consensus, but actually it is more complicated than the one we just talked about. So it has 5 components, but I will use Bitcoin, for example, to show you how it represents BFT consensus in the first place. So the consensus protocol Bitcoin uses is called the Nakamoto consensus, because this is the guy who wrote this white paper. So the consensus, you need a target. So what is your target in Bitcoin system? So since you are making payments, we are using transactions to serve as a request. And at the same time, the block is also our consensus target. So the argument is, if you agree on this new block, so then every transaction included by this block will be naturally included. So the idea is to serialize blocks, we serialize or finalize transactions. So the first step of the consensus of Nakamoto's is we have to work on the new block. The new block should include all the transactions. So as a node, I can receive new transactions from clients. I collect those unconfirmed transactions, and then I put them into my working block, and this block looks like this. So at this moment, you don't have to worry what does it mean by each field. So basically, I choose a block to work with, and before that, I will include my recent transactions from clients into my block. Again, okay. So next is which I think is the most important thing in consensus of Nakamoto is we have to make this block valid. So in the previous slides, you can see that we have the block is your working block. I want to make it valid, so which means I'm working to find something, find a nonce to be determined, so that if I find a nonce, then this block should be ready to be broadcast to the network. So basically, how do you find such a nonce? Say this is a block header containing 6 fields and version number, previous hash. So this is the previous block you have to attach to. The Merkle tree root is basically the digest of your transactions. Yeah, those are fixed numbers, a fixed value. Time is your current timestamp, and then what is most concerning for us is difficulty and nonce. Basically, to make this nonce valid, you have to find the nonce so that the double hash of this entire header should be less than or equal to a certain value. So this value is determined by all the 0 bits in the prefix of the difficulty. So basically, what does that mean is you have to continuously rehash for different nonce until you find one such that the output has at least this amount of zeros. So as you can see, this is a very difficult process if your difficulty level is very high, or you have more prefix zero requirements. So this is why you may heard that Bitcoin mining is consuming so much power, and this is a culprit. So, so the idea is to make the entire network mining at the same rate. Every 10 minutes, you can, on average, 10 minutes give you a block. Then, no matter how large your system is, the protocol states that the entire network can mine the block for every 10 minutes. So basically, the difficulty is dynamically changed so that no matter how large your network is, even if you are running if you are running your system with quantum computers, it's still 10 minutes. It's designed by the protocol. It's not scaled up with the computing capability. So because of this, people are arms racing in terms of mining power. So as I recall, the total mining power, mining energy consumed by Bitcoin network has already exceeded the power of the country of Finland. So it's country level power consumption, which is not very sustainable, but some people argue it is necessary to guarantee this anarchy provided by Bitcoin, which some people think it is important. All right. So the next thing for consensus protocol is once you have such a valid block, you propose that to your neighbors, and throughout the process, you propose to everybody in this network. So you can use gossip. I think gossip usually means you propose your block to neighbors and neighbor to their neighbors until everybody has it. So the next thing is how do we have agreement on this block? So the agreement used by Bitcoin is really simple. It doesn't actually use any kind of a message exchange at all. It's just based on your personal, it's not personal, it's on your own judgment on the current state. So whenever I see a new block, if it is valid and extend my longest chain, I will ditch my current block and switch the new block. So that's unfortunately, if everybody if everybody produce a block faster than you, then you have to give up to work on the new longest chain and rerun your hash algorithm to find the new block with a higher height. So this is like a brute force, very simple idea of consensus, which is known as the longest chain. So by doing this, as long as more than half of the network follow this rule, then we can guarantee probabilistically that the longest chain is a consensus. So more than all the honest ones, miners, we are working on the longest chain, the same longest chain. So this is the key, I think, key safety provided by Bitcoin. It is based on the raw power consumption and the kind of a conscience that the longest chain is our target. So, but in this case, what will happen if two valid blocks of n-1 are received? So this is unheard of in BFT systems. So if I receive two blocks, both are valid, both are at the same height, how to deal with that? So this is a new situation BFT doesn't deal with. So this is known as blockchain forks. Whenever you have this, it's very likely the network is partitioned into two groups, one following this block, one following that block. So to break this stalemate, you have to let them compete until one of the group is the first to propose a new block so that the green partition will win and blue partition will fail. So in this case, we are still following the longest chain rule. There's not tricky stuff to deal with this. It's all based on the raw power of the participants. So this is the how longest chain works. So by the end of the day, we have this huge power consumption issue because longest chain rules for everybody. And lastly, I think this is like a secondary concern for Bitcoin, for consensus is the miners get rewards for block mined. So, but the rewards will diminish for every 4 years. At the end of the day, when after the year 2040, so we don't have, there will be no new Bitcoin mined, so there will be entirely benefiting from transaction fees. So this is actually the Nakamoto's consensus protocol, and we're gonna skip this because this is not very relevant in terms of consensus comparison. So the question is, does Nakamoto consensus realize BFT SMR? So the answer is sort of. I can make this comparison. The safety and the liveness are basically the same, except that Nakamoto going to give you a probabilistic finality, but BFT SMR gives you the deterministic finality, because the longest chain rule is based on raw computing power. If you suddenly have a quantum computer that can rerun this longest chain all the way from the backward side, then that will be the new longest chain. So which means that the finality is not deterministic in Bitcoin's case, but we are counting on everybody to run to their fullest potential. So we hope that scenario will not happen. So, but one more thing about it's a fairness situation. We want Bitcoin miners to contribute to new blocks based on their computing power, which is not the case. It's not heard of in BFT protocols. But generally speaking, they are quite similar. Bitcoin realizes one form of BFT SMR, and because of this, people are thinking to themselves, we can basically apply classical BFT SMR for blockchains. I don't want to use Bitcoin's Nakamoto consensus to waste energy. So that basically jump-started the research from the new interest in BFT research in the early 2010 to current day. All right, so I'll skip this more detailed thing and talk about what I think is the most interesting onwards. Yeah, I have maybe 2 or 3 minutes. Okay. So for consensus in emerging systems, the thing I'm currently working on is, this is not my paper, is use consensus on real-time systems. So because in real-time systems, if they work, if you have a list of sensors, a list of replica or processors, list of actuators, you want the processors to agree on the same inputs. So you may have replicated sensors, but you can only agree on the same sensor inputs to make the same action to the actuator. So this is actually a redundancy scheme that guarantees the system will always work as planned. The second application is actually I've been using blockchain and consensus to help the several 5G or industry companies to deal with this spectrum allocation. So spectrum allocation used to be done by FCC on a centralized planning scheme. But the government, now they wanted to simplify the process and let the markets dealing with this scenario. So we propose to use a blockchain and a consensus-driven scheme to help to allow that each spectrum user can request a spectrum license in real time using blockchain. So although the throughput is not very high, but we'll continue to work on that to improve the throughput and latency. So another thing we have been working on is we are designing new consensus scheme based on the common subset consensus to deal with decentralized machine learning. So this is one type of machine learning known as federated learning, that all the different nodes should collectively work to train the same model. So we are trying to integrate consensus protocol into this process so that this decentralized federated learning agents can work on the same model and update the same model and retrain in the iterative manner. So consensus is our choice. So because I don't personally, it's not personally, sorry, I don't want to involve trusted third parties to do the aggregation, to do the model storage. So if they can do that without central server, this would be great for democracy, for privacy, and so on. So this is my last slide. So the last thing we're dealing with is we're trying to build consensus protocols into drones. So why we are doing this is because we have Kentucky as a state. We suffered from natural disasters in the last 2 years, and drones happen to be a very good source tool for reconnaissance for disaster relief. But very often cases, you cannot always have a central commander controlling all the drones because this will be a single point of failure. So what we imagine is different UAVs or drones, they should communicate with each other, do their own path planning based on consensus, not based on some central commanders. So by doing this, we are actually integrating real-time consensus protocol for UAVs so that it can do their own path planning and model training and collision avoidance and come back to their respective paths. They don't even have to come from the same aircraft paths in the first place. So I think in my PhD student and another undergrad students, Cameron, you are here. So we are dealing with this case. And lastly, we are trying to use consensus for decentralized identity for infrastructure, which is relevant to our spectrum management scenarios. All right, that's the end of my talk. Thank you.
We have time for questions. Any?
The Lamport algorithm applies when you have a 0 or 1 result.
Mm-hmm.
What if the result is not binary? It seems to me that if the commander
Mm-hmm.
Can give 0, 1, 2, 3, or 4,
Mm-hmm.
then and can be compromised, then the algorithm fails to work. So when you're talking about sequence numbers,
Mm-hmm.
Clearly that's not a binary decision.
Mm-hmm.
How do you then expand the Lamport algorithm for non-binary situations?
Yeah, to dealing with non-binary value consensus, there's a line of work known as the multi-value Byzantine agreement. So what they do is they basically decompose multi-value agreement to binary value agreements. So as for the details, I don't know. Maybe I'm not very familiar with that. But for the SMR situation, so you can think of this in this way. If your value has a valid signature, so this will be considered as 1. So if your other value or value with a different signature or doesn't have a digital signature, this will be considered as 0. So in that case, so the SMR situation is trying to split the multi-value case into just 2 cases. One is a single value with a valid signature. The other one is either no value, no signature, or invalid signature. So yeah, one thing I forgot to mention is for SMR to work, you really have to have digital signatures. But for Lamport's algorithm, you don't have digital signatures. Yeah.
So digital signatures solve the problem, because if you've got a Byzantine failure,
Mm-hmm.
Digital signature is not going to detect that, right?
Mm.
A Byzantine failure doesn't have the private key to create a digital signature somehow?
Yeah, it's like a Byzantine node. If they sign on something, even if they are Byzantine, they should produce a valid signature. So otherwise, yeah. Yeah, it's kind of it takes some time to answer this question, but the general idea is if you have digital signature, then this signature will allow them to detect equivocation. So, because if you want to equivocate, then your digital signatures will be served as a proof, so other people will find out you are equivocate based on the 2 different signatures. So, yeah, by doing this, they are only dealing with 2 situations: a valid value proposed with a signature, or a different value which is not used by the quorum. So this is how it works. Because only one, this one quorum will only supports that single digital signature value. So no other valid quorums will support this, the different signature scheme, different signature value. So I think that's my interpretation of this, how it was translated. Maybe I'm deviating, I'm obviating some other details.
One more question. Any question? We still have a few minutes. Well, actually 1 minute. All right, if no questions,